Air pollution. It's this massive, invisible problem, right? We know it's all around us, but what if you could actually see it? Like everywhere on Earth updating every single hour? Well, that's exactly what we're digging into today. A really cool new approach that uses AI to map the air we all breathe.
All right, let's kick things off with a number that is just wow. The World Health Organization says that 99%, yeah, 99, of all people on this planet breathe air that's considered unsafe. We're talking about pretty much everyone. It's a huge global problem. So here's the catch. To tackle a problem this big, you need data, right? You need to know what's going on. But our physical monitoring stations, well, they're just not everywhere. They're super expensive to build and run. So we end up with these huge gaps in our understanding. It's like trying to navigate a giant dark room with just a tiny flashlight. We're pretty much blind in most of the world.
So that brings us to the big question, the whole reason we're here. How do we fill in all those blank spots on the map? How can we see what the air is like? Everywhere, all the time.
All right, section 1. Let's really get our heads around this global blind spot. It's a huge, planet-sized issue, and we're trying to solve it with just a tiny handful of data points.
So the really clever solution here is this idea of a synthetic sensor. I love this concept. Think of it like a digital detective. It's basically a machine learning model that's been trained to act just like a real monitoring station. It takes all the clues it can find and figures out the pollution level in places where we have no sensors at all. It's a total game changer.
Okay, so how do you actually build one of these digital detectives? What kind of clues does it need to start solving the mystery of the missing pollution data?
Turns out it needs a lot of clues, 26 different kinds to be exact, and they basically fall into 4 big groups. You've got temporal data. Is it morning rush hour? Is it summer? Then there's weather data, wind, rain, temperature, all that good stuff. After that, you've got satellite data looking down from space. And finally, emissions data. Where are the factories? Where's the traffic? Things like that.
The AI model, which is called Light GBM, by the way, its job is to take all 26 of those clues and mash them up against millions of real-world pollution readings from actual stations. And over time, it starts to learn the super complex patterns, like how all these different things connect to each other.
Okay, but here's the real test, right? The million-dollar question. It's one thing for this AI to work in a place where it has some data to learn from, but what happens when you drop it into a country it's never seen before? Can it still figure things out? Which brings us to section 3, the model's report card. Let's see how it did on its final exams.
First up, the baseline test. Take this one station in Spain. When the model has already had a peek at some data from that station before, it does great. It gets an R-squared score of 0.81, which is basically like getting an A on a test. Excellent performance.
But look at this. This is the exact same station. But this time, the model was trained without seeing any data from Spain at all. And the performance just falls off a cliff. The score plummets to negative 0.03. That's not just an F, that's worse than just randomly guessing. It's a total failure.
So what happened? How does it go from being a straight A student to this? Why does it fail so spectacularly when it's somewhere new?
Well, it comes down to a really key difference between two things, correlation and bias. Here's what the model gets right. It's amazing at spotting the pattern, the rhythm of pollution, the daily ups and downs. That's the correlation. But here's what it gets wrong. It struggles with the actual level of pollution. It doesn't know if high for this new city means a level of 50 or 150. It needs some local data to ground it. That error is the bias. And you can see this trend perfectly right here. This chart for NO2 shows it all. The baseline test, great score. Predicting a new station inside a country it already knows, a little worse, but still okay. But then trying to predict in a brand new country, whoosh, the score just tanks. That bias is the big problem every time. Okay, so the model has a pretty big flaw. But, and this is a big but, that doesn't make it useless. In fact, this is where things get really, really interesting. This weakness, this limitation is about to become its biggest strength. Let's head into our final section, mapping a clearer future.
So you might be thinking, if the model can't get the numbers right in new places, what good is it? What can it actually show us?
Well, it can show us this. It can create these absolutely stunning, high-resolution maps of air pollution for the entire planet, updated every single hour. Remember that blurry, spotty map we started with? This model turns that into a full-blown, high-def movie of the air we breathe.
And with these maps, suddenly we can do all sorts of incredible things. We can see pollution hotspots flare up in real time anywhere in the world. We can figure out the annual air quality for more than 261,000 different places. And maybe most importantly, we can see which specific pollutant is causing the problem in any given region. This is a huge, huge leap.
And this is what leads to this really wild, kind of counterintuitive idea. The model's biggest problem, the fact that it's uncertain in new places, that's actually its greatest strength.
Just think about it. You've got a limited amount of money to spend on these expensive physical sensors. The world is huge, so where do you put the next one? How do you decide where it's going to give you the biggest bang for your buck?
The model tells us it can literally create a map of its own confusion. It can show us the exact places on Earth where it is least sure about its predictions. And guess what? Those are the perfect spots to build our next sensors. So the model's uncertainty becomes a roadmap, telling us exactly how to get smarter. It's brilliant. And that leaves us with one last big idea to chew on. This whole approach isn't just for air pollution. Think about other huge global challenges, climate change, disease outbreaks, you name it. What if the key isn't to get rid of uncertainty, but to map it and then use that map as our guide to understanding the world a little bit better?